Hi friends, welcome to my channel Phy-LAB, and today we are going to discuss about Kirchhoff's law and mesh analysis. In ISC, most of the time we would get a numerical problem from this topic, at least of 4 marks. Kirchhoff's law consists of two basic laws. One is called as Kirchhoff's current law or Kirchhoff's first law, and the second one is called as Kirchhoff's voltage law or Kirchhoff's second law. Kirchhoff's current law states that the algebraic sum of all the incoming current at the node is equal to the algebraic sum of all the outgoing current from the same node. Whereas Kirchhoff's voltage law has to state that the algebraic sum of all the potential drop across the closed loop is equal to 0, or the sum of the potential drop across each component in a loop or mesh must be equal to the algebraic sum of all the source voltages. Kirchhoff's current law is based on conservation of charge and is applicable at nodes, whereas Kirchhoff's voltage law is applicable for mesh or loop and is based on conservation of energy. I would like to highlight over here that this conservation laws on which the Kirchhoff's law is based on is very useful for ISC examination. You would often get 1 mark question stating on which conservation law is Kirchhoff's current law based, or on which conservation law is Kirchhoff's voltage law is based. Here you can see a one question that I have given you to find out the current I given in each mesh. Now if you notice here, I have got 5 ampere current reaching to this node, 7 ampere current reaching to the same node, and 2 ampere current also reaching to the same node. So the incoming current at the node happens to be 7 to 9 and 5 14, while the outgoing current from the node is I plus 3. Similarly, 14 must be equals to I plus 3. Thus the net current I must be 14 minus 3. That gives us 11 ampere as the answer. You can try the same on this question. Let's move on to the next slide now. Now combining the Kirchhoff's current law and combining the Kirchhoff's voltage law in solving the numerical problem, I frame a law which is often called as mesh law. This makes our work quite easier. Remember, Kirchhoff's law application is in those numericals where you find more than 2 batteries connected in parallel, and also these 2 batteries must not be of equal magnitude. The EMF must vary. Here you can see in this problem I've got 4 volt and 2 volt, and there is a mesh. Okay, now let's see how one should apply this law. You should always choose the battery sources present in the branches to draw the current. So here you can see I have got a 4 volt battery and a 2 volt battery. So what I'm going to do, I'm going to draw the current from each battery in each of the terminals. So from this 4 volt battery I will draw the current, and remember the current are always drawn from the positive terminal of the battery. So from the positive terminal you can see I have drawn the current I1. Now this current is going to run in this entire loop. So I1 running over here, and definitely the I1 was there in this branch, so it is going to come as I1, and it must be coming from this end. So this is the I1. So in this entire branch in which the battery was connected, I have drawn the current I1. Now if you refer, the second battery I have got as 2 volt. Now taking the 2 volt battery, again I will draw the current leaving from the positive terminal of the battery. Now this is the positive terminal, so the current has been drawn I2 in this particular direction. Now from here the current will leave for this particular branch. So this is I2. In this branch the current is going to remain I2 is going to remain the same everywhere. So I2 over here, and similarly the current must be coming from I2. So in this entire branch I have distributed the current I1 I2, sorry. Now at point D you can see I1 is coming from here, I2 is reaching from bottom. Both the current add at this point D, and the sum together of these two current, that is I1 plus I2, goes into the branch DC. That is how one should first distribute the current in the entire branch. Now, depending upon the number of current variables, one should choose the number of meshes. Now, what is a mesh? I've already discussed in an earlier video, so you can look into those in those videos to get the exact definition what is a mesh or a loop. So if you notice, I have got two variables. One was I1, another one was I2. So I'm going to choose two meshes, and these two meshes are going to be, you can see the mesh I have highlighted. So from here, A, then I would go to D, then I would go to C, then I would go to B, and then again I'm going to go back to A. So the direction of traveling in the mesh is A to D to C to B and then to A. So that is the direction of travel in the mesh number 1, which I have taken into consideration. Now the second mesh which I am about to take into consideration will be this one, which is now highlighted. Now you can see this mesh starts from D, and then I am going to travel to E, then I am going to travel to F, then C, and then back to D. Remember, mesh must be closed, so your starting and ending point must be same. So I start from D, goes to E, then to F, then to C, and back to D. Now this also gives me, while choosing the mesh, this also tells me what will be my direction of travel in that particular mesh. Now this direction of travel is going to be very, very important. Let's see how. In this step number 3, if you are traveling in a mesh and you meet any circuit element, especially that circuit element in ISC is going to be your resistance. So if you are meeting a resistance and you are traveling along the current, now notice here I have just put this N highlighted. So if you are traveling along the direction of current, then the potential drop of the circuit element must be taken with a negative sign. So here this is the direction of current and you are traveling in this direction. Both you are traveling along the direction of current. Remember, the potential drop is going to be minus, written with a negative sign. So the potential drop across that resistance will become minus IR, and vice versa. That means if you are traveling opposite, so if you are traveling opposite to the direction of current, traveling opposite, again see this P has been highlighted too, just to give you that remembrance during your paper that it must be a plus IR. Am I clear at this point? Let's move on to the next slide. So step number 4, while traveling in a mesh, if you are meeting, or if you are entering, not entering rather, if you are exiting the battery, you should always take the sign of the plate from the side you exit the battery. Now in this case, if you see, my direction of travel is this and I am exiting from the positive terminal of the battery. So the EMF of the battery would be written with the positive sign. So whatsoever the EMF is, I am going to write down that EMF of the battery with a positive sign. Similarly, if in this particular case, in the second case, you can see I am traveling and I am exiting the battery from the negative terminal of the plate, so I am going to write down that potential drop or that EMF of the battery with a negative sign. So remember these simple steps of direction of travel and the earlier things that I've told you. Now then I need to frame the equation. Now which was the mesh we have taken? This was our direction of travel, let's say A to D. So this is the point A, then to D, then to C, then to B, back to A. So while traveling from A to D, I am traveling along the direction of current and I am meeting a resistor. So the potential drop will be minus 5I1. Now when I am traveling from D to C, I am traveling along the direction of current, and therefore the potential drop will be minus 6 I1 plus I2. And now I am moving to C to B. Again I am traveling along the direction of current, and the potential drop in this case will be minus times of 4 I1. And now when I am moving from B to A, again I am moving along the direction of current, and I meet again a resistance. Now see over here, this resistance happens to be a internal resistance of the battery. It does not affect any way around whether the resistance is internal or external. Do not get confused. Treat it like normal resistance. Again you are moving along the direction of current, it is going to be minus 3I1. And then while moving towards point A, remember I am going to exit the battery from the positive plate. Now since I am exiting the battery from a positive plate, it has to be plus 4. So that frames my equation: minus 5I1 minus 6 bracket open I1 plus I2 bracket close minus 4I1 minus 3I1 plus 4 is equals to 0. You may like to give your try for this second mesh, D, E, F, C, D. Give a try, frame the equation, and then just in a second I return back with the equation. Now, probably you must have framed the equation. Let's check it out. I'm moving from point D to point C. So it has to be, I'm moving along. If I'm moving along, it is going to be minus 6 I1 plus I2. And then since I'm moving C to, sorry, then I'm moving from D to C. Sorry. I'm moving from D to E. Okay, now when I'm moving from D to E, I'm going against the direction or opposite to the direction of current over here, D to E. Now if I'm traveling D to E, I'm moving opposite to the direction of current. It's positive, so it's going to be plus 5I2. Again, when I'm moving from E to F, now when I'm moving from E to F, you can see I'm going to leave the battery from the negative terminal. Since I'm leaving the battery from a negative terminal, it's going to be minus 2. Again, then I move, encounter a resistance opposite to the direction of flow of current. It's going to be my opposite, so it's going to be positive plus 1 into I2. Again from F to C, again going against the direction of current, it will be plus 4 I2. Again moving from C to D, I'm again going the direction opposite to the direction of flow of current. It is going to again plus 6 I1 plus I2. So that gives us the equation along with the sign. See whether you have got it correct or not. Now then what I need to do, I need to solve these two equations simultaneously to get the final result. You can try out some of the questions over here. This is one of the good questions, you may give a try. This is another very good question, you may give a try. The currents are already marked for your conveniences. So these two questions you can give a try. They would help you to master Kirchhoff's laws.